Okay, so let's start. So today we're going to change tracks and look at something slightly different. So some basic notions in learning theory and then where some concentration like things come up. So one sort of a generic problem is the following. So it's something like this. So let's say that there is there's a class of functions. Okay, so some class of functions, and so they are from some omega to r, let's say for now, and we obtain IID samples from omega according to some distribution D. So let's say n IID samples. Okay. And there is some kind of figure of merit or something. So there's something we would like to say about the whole class. So there's some property of D more or less. So basically, so D has some property, and maybe this is maybe we want to compute some expectation over D or something like that, or find the function that the best possible expectation, the highest possible expectation over D from this class. But all we have is access to this empirical, these samples. So whatever we can do, we will do only on these samples. So we can, but otherwise there is no restriction. We have this class that we get these NID samples. Then we can evaluate potentially. We can take each function and evaluate it on this. And based on that, we make some decision. We say, okay, this is the best function, something. And then we want to say, but that's what we got from the empirical sample. And there's something that happens on the actual D. So there's maybe some kind of expectation factor. And we want to see how far can we be. Okay. So the kind of question is, so this is a very generic question, and many things can be put into this form. But let us just see, kind of see what sort of thing is this, that estimate some property of measure based only on. So let's say these samples are called X1. So they're given only. So what kind of, so in one very simple thing, which is all we're looking at today, but you can try to see how later on other things can be put into this framework. So for example, what is say soup F in an expectation? So this is some property of both the family F and D. And so what the natural thing to do? The natural thing to do would be to just take the function F, which is maximizing here, and hope that that's the best. Okay. So this is what you want to study. You want to understand when basically when you use something with finite samples, when and on what based what conditions on F, etc., can you get good result for things like this. So how many samples? Should be needed for a good answer. So right now it's very abstract, so let's make it more concrete. So let me just so let's look at a concrete example. So let's consider F to be this class Lipschitz 1 and this coordinate Lipschitz 1. So it's like
it's all those functions f from 0, 1 to r, such that fx minus fy, so they're Lipschitz. And let's, for technical simplicity, it's not such a big thing. Let's also put that, and f0 is equal to 0.
So this is a uncountable infinite class. And so, and let's think of our previous examples, maximizing expectation, or something. So what we would want to, so let's say, so okay, so what we would want to is supremum over all f, of, let's say, something like okay. Of course, this is a random variable. So let's say we want to look at what is it in expectation. You want to understand how big or small. Okay. Is there a problem here? Sorry? No. Sorry, what? No, yeah. So let me say I'm different. I want to study just this. So I want to say how, like, so what is the thing? The thing I'm looking at for all functions there. I'm looking at the empirical average and the actual average. What's the difference between the two?
So the example was with the soup inside.
Yeah, but let's see, suppose I have things like this. Then I know that for everyone, so suppose it's not an expectation thing, but with high probability is small. Then for every function, the empirical mean is close to the actual mean. So if I take the one with the highest empirical mean, that's also the one. I mean, close to the value is close, it's close to the one. So it's all that problem also.
This is stronger than.
Is it fine?
Yeah, but it's stronger than.
Yeah, but we just so let's
So it's called the idea of uniform convergence.
yeah. So this is like, this is sort of like, yeah, so it's uniform in the sense that you need uniform over. So everything should be small. Everyone should. Okay. So yes, so this kind of thing comes up again and again. If you're looking at classification and stuff, like this is the kind, I mean, like this is really the problem of learning in something. You know, always in learning, what I mean, something of this kind will be the thing. Maybe you put some other context on top of this and so on. But always it will be something like that. You get combined samples, you do some optimization on net based on just some time, and then you want to see. So there will be some value there. There will be some value actual expectation, and that's the that's the correct thing. And then you want the direction to be small. So there's like a difference. We can think of it as the difference in the training error and the actually, yeah. So, or generalization more. So all of these things sort of become problems of this kind. So it's a very sad, it looks special, but these kind of things can be very, this is the fundamental problem. So there are many methods, many kind of tricks. We'll look at some of them. So of course, I mean, like, by what when I said all these general things, that's not for this class. I mean, the class will keep changing. So this F will keep changing, but yeah, but then you'll be very okay. Okay, so yeah, so this is what we want to study. Okay, so how would we do this? So one more thing is that, so suppose that we show that the expectation is small, is there also concentration? Suppose somehow you know that the expectation is actually somehow small, or whatever it is there concentration around this expectation? So that's a question. That's actually an exercise. The question. So does so
Okay, so this is something to think about.
Claims that you know enough to answer. Okay. Yeah. Okay. So yeah, but for now we just complete the expectation. So the expectation is small. Answer to this is actually yes. And so if the expectation is small, you're concentrating around something. So things are fine. So, but the trick is the doing concentration is actually not so hard. Point is, you can apply the boundary difference in the potential. But the thing is to show that this expectation itself is small.
So okay, so how should we go about doing this?
So if this soup was not there, it was just one edge, is this expectation? Suppose there's no, suppose F has just one element. It's just the fact that F concentrates around the expectation. So that means that, and you're not it's so of course it's like concentrates extremely well. There is a suboption. So that will imply that the expectation also has to be small. How small?
Really small.
So this actually you don't need to put constant. This is like some basic. So you're doing and so these are basically bounded random variables you're taking. So just the variance of this quantity is about 1/n. So that's what you expect. So it's like so the deviation should be most 1/n.
So we expect so just from standard arguments.
So roughly 1/10 or just
If there is a concentration for a single level, and you have, let's say, a probability that the inner thing is deviating by epsilon is exponential.
no for each F. Yes, but there's a group inside F.
But you're talking only about a single level, right?
Yeah, but now, yeah, so this this solves the problem. For single expectation can be at most 1/2 just by standard variance forms, or even just
But it is much stronger than that.
not much.
So for a single F, you say that the deviation of the sample average from its mean
Is
is at
about-
least it is at least epsilon. Okay?
Yeah.
So that event is at most some concentration and exponential.
Yeah, the concentration is much, but if you look at the expectation,
Yeah.
so it will be of the order of sigma, right? And sigma is going to be like 1/. Even if it is a Gaussian. Wait, what am I saying? Yeah. I mean, so if I'm looking at this expectation, I mean, so
Oh,
right, so just okay, so forget about the thing. Suppose I just square it.
yeah.
Then this is just the variance. Right, and the variance is 1/n, or at most 1/n. That's all.
So you're saying 1/√n is some of right?
Yeah. Yeah, I mean, so basically, yeah. So another way of saying it is if I had n samples, so if I wanted error epsilon, I would want 1/epsilon squared. That's what I want. That's what the concentration what goes to tell. So to get error epsilon, I would need 1/epsilon squared samples. Then the error probability I can decrease very fast. There are two things. So basically.
And the concentration result will let you do the error probability thing much faster. So get error epsilon with probability delta. One minus delta, it will be 1 over epsilon square log. But the 1 over epsilon square you can.
So both of them are slightly confused. So what is wrong with this argument? So let's say that you have a subversion concentration. You split the expectation over two units. One where the deviation is greater than epsilon. And one.
No, so just suppose you apply the usual constant inverse. So that's the probability is 2 times exponential nt squared, something like that.
Yeah.
So nt squared has to be something less than 1.
So
nt squared has to be
what is t?
So t is a deviation.
T is a t.
But there's an nt squared. So how many samples do you need? So
You're looking at all that.
yeah. So to get any kind of error probability which is non-trivial, I need at least 1 over epsilon. Then I can make the error probability go down very fast by just adding log everything. So the 1 over epsilon square you cannot right.
Okay. So it doesn't change anything. So it will be like b times e power minus n t squared.
Yeah.
Plus t. That will be a bound on the expectation. If you split it into two units. So now you optimize over.
Yeah, but t is already there.
So, but now you optimize over t because t was an arbitrary point.
Let's see. So this bounded case. I think this will be the no matter what you do. I mean, this calculation. Yeah, you can't give this thing. This variance is also concentrated. I don't know what. So what is this? Is the probability that it deviates by more than that? It is that it is. And otherwise,
that,
no, so no, that's the error. Like, if you're not at t, if it does not deviate, no.
I mean, there are two events, right? One is controlled by t.
Okay, so t plus
T plus e to power e minus n t squared.
Yeah.
So now you optimize over t.
Yeah, but how will you get anything better than this?
No, I don't know.
Yeah, you should not, because just think about it. So because just to make this thing even up, so t is the threshold. So suppose I want to make a threshold, if I make a threshold 1 over root n, this thing is to give me a constant.
Yeah.
So if you make t very small, then the other one will be a constant.
I get some kind of transcendental equations.
No, but it's the thing, it should not be doing the equation. Just think about it. So it's like 2 to the power minus e power minus t squared, and you want to make t very small, right? To make t very small, this nt squared is 0, and then that thing is giving you a constant. So no matter what, so you get constant deviation. You want something decaying in. You get something decaying in.
But normally, even if you optimize that boundary thing, you will not get better.
Yeah, I just giving you the proof that you will not, because I just so like you take. So I mean, to get something better, you will have to be very small, right? Smaller than 1 over root.
Yeah.
If I make t smaller than 1 over root, then nt squared that term is very hard. Okay, so right, so yes, so then this is what we expect for one. So what do you think will happen for the whole class? So how should we? Suppose okay, now let's say so for one thing it is 1 by root n. Can we do some? Can we? So can we do something for larger? So for one function is this. Two functions, what happens?
Certainly. Okay.
Yeah, exclusion of that.
Is that because concentration plus area bound?
Yeah, it's concentration plus union bound. So like you keep working. And in fact, yeah, so this is one thing maybe I should have done earlier, but this is a thing that you can prove basically using the same argument to transfer the strength. Make that if you have
so generally if x1 to x K are sub-Gaussian random variables. So let me just call it K sub-Gaussian, which means that is probability that xi is bigger than t is less than some then the expectation of the soup
They may not be independent. So yeah, so this basically will. So how will you do this? So the way to do this is to say, so you basically take a union bond over these guys. So you say, so again you put a threshold. What's the probability that they all go above the threshold? And what's the, and if they're below the threshold, then it's you can get it. The probability that at least one of them goes beyond the threshold is a union bond over k constant, which all is like e to the power minus k. That's the root log. And then when you optimize. So this, what does this tell us? So this tells us that if
if C so if you look at C subset of so this is some finite subset of F, then E so
okay. Why is this?
Hi, sorry, is this mistake in this one, the expectation of soup?
Why?
C1 K,
Yeah,
K1 looks a bit, K looks a bit too big, no, maybe I missed.
no, K is the capital K is the sub-Gaussian.
Oh, yeah, I think I got.
Yeah, sorry, yeah, so let me not call it K. Okay. Now, so why does this follow? So if it's a finite set, this means finite set. So it's a finite set. Then this is coming from here. Why do I get right nu is equal to 1 by root n? Yeah, that's basically just the fact that each fxi, because it was bound between 1 and 1, it's constant sub Gaussian. When you sum it by n, so it's root n sub Gaussian. That is equal to easily, and when you divide by n, it's 1 by root n. Or you can just recall okay, so this is fine, but is this useful for us? What is our setup? What is it? It's uncommon. All. So this is not so. So what should we do then? Yeah, so put so-called epsilon net. So you put a net of function, like a finite of function, that every function is somehow closed close in some distance, and there should be some natural distance that is a useful distance for the curve. So what is the useful distance?
Yeah. So we should try to find a C such that every Fn is somehow somewhat close to some element. So these things are called epsilon nets.
So enter this name.
So we enter. So for our setup, the natural metric is the supernormal.
Okay, so suppose that we had some.
So usually, usually, as a notation, the size of the smallest such is usually denoted this is the distance, and often this is dropped, right, because it's clear from the
So just talking inside. Okay, so now right. So suppose we have an epsilon net. Then can you give me a better bound like this, or some bound that uses epsilon? Or can you give me, so given epsilon net, can you give me a bound on this side? I mean, of course, this is where in terms of the size of the epsilon net.
and maybe the epsilon.
Should be like twice.
Yeah.
So what should we?
Find some function in the epsilon net which is close to
Any f? Yeah.
any element. And then you
Then take a difference of that.
So let me just write the these obvious things. So at least this. So I can also write fxi. Let me keep writing that. I mean, they're all IID. So
Okay. So the first one is obvious because for every so I'm taking a supreme over all. So take any f here, there is somewhere here which is at most 2 epsilon. So the equality is. So any element here is at most this plus 2 epsilon, and therefore the supreme also is less than that. And so we take expectation of both. And this we already, where it is finite, we solve. Okay. So the quantity we need. So the upshot of all this is that. Let me write it here only. Okay. Yeah, but I can take the best. So now the goal is to construct some epsilon. So let's see. So what's the how will you construct an epsilon net for this? Just because now if we so far you're not using both the function classes. Function class is lifted function from the 0 to the real number. One lifted function. And f0 is equal to 0. Yeah, piecewise and linear. Yeah. So how should we think about it? Dyadic fashion.
Kings on similar thing on
So I want to get an epsilon. Some fixed epsilon is given to me.
Yeah, okay. Yeah,
Yeah, so you grid the whole thing by 1 over epsilon. And then what should you do? So what kind of functions?
Like
So let's say this is like it'll be helpful to think of it as epsilon by 2. Okay, so now what kind of function should be there?
all the functions are bounded by 1.
Sorry?
All functions are bounded.
Yes, that's why. Yeah. So that this is the only thing we do. Yeah. But there is more.
f of 0 is 0, so you always start from
Yeah, and then.
And then you either go straight or up or down.
Yeah, so yeah, straight up.
So all functions will look. Yeah. So it can be like this, or like maybe this, or like so. This, right? So things like this. Yeah.
Only such functions. So how many such functions are there?
3 to the power. So the 3 power distance.
So at most 3 to the power of that.
Yeah, 3 to the power 2 by epsilon. I think. So, yeah. Yeah, so let me just think that, yeah, so assuming the number of such functions is at most well, if it is an integer, otherwise,
Yeah,
yeah.
if one epsilon is integer, I think.
Yeah. Okay, so but yeah, now the question is why is this an epsilon vector? So given any function, what can you do?
Look at its value.
Grid points, and what can you and then
Find function.
it is how far?
Within epsilon.
So like 4 actually, take the closer.
Yeah.
So it's just it will lie, so wherever it lies on the, so if it lies, if the value here lies somewhere here, then you choose this one, lies here. So you basically round it to the closest multiple of epsilon by 2, and so you get epsilon by 4. Um, so the proof sketch is that there exists for every
So where you have to use the quadratic Lipschitz.
yeah, so that's where yeah. But yeah, so that's the thing. So where are we using this? Actually, where are we using this? Yeah.
So we showed that at the grid points, the distance is that much epsilon by 4. So we want to show that that is that everywhere that's that much. That's why you use.
So we can show the grid point function is in this class. If you put the grid points. So the grid point
So your function f tilde, your function f agree is close to f tilde on the grid points. And you want to show that in between also it is close. Then it not straight. I can't be like go up and come back down.
This also has to be like this. Yeah, well, yeah, on all the so the grid actually, yeah, so I have to be somewhat careful. There's a grid. I mean, I have to go to the one thing also, but so these are the grid points. And so the question is why is this way? So firstly, if suppose such a thing exists, then is it clear that it is epsilon? Suppose this is useful, then it should be clear that it's epsilon. Why? So you have so what to do? So first of all, is it clear that every function here is Lipschitz?
Yeah, that's all.
That is. Okay. So now from that and this, we will follow the reference on it, because take any other point y, right? So y is somewhere. So let's say y is here. Right? So it's at most epsilon of 4 to either this grid point or that grid point. So you go to that grid point. At that point, you know that the difference is epsilon by 4, between the two functions. Now, we have to move at these level epsilon by 4 for the f phi and for also f tilde. Both of those can contribute at most both are limited from. So you get C epsilon by 4, it's at most epsilon. Okay. So if this is true, it is an epsilon. So why is this true? So it was basically say that this function, this rounded function, is in this class. Right? It's basically a Lipschitz. It is a Lipschitz. And why is that?
So the only thing which can happen is that maybe there are two nearby points which get grounded too far away.
Yeah, which cannot happen in this. So that's the thing. So all we have to show is that so basically, I mean, you can think of it as some kind of induction. So in the beginning, of course, so you can start constructing the set like this, right, by just rounding to the closest. And so at the beginning, it is correct. It is such a function. It's like a starting sequence of one such function. Now you get to the next point. So at next point, the value is somewhere. So, but where could it be? So it's either in only in this segment. Yeah. So if it is this part, then you're going to round to this. Otherwise, if it's in this part, then you're going to round to it. Whichever one you get, it is correct. So now the tricky part. Right? So now the thing is that you have rounded. So but when you rounded, the difference was epsilon by 4. Right? And then you move epsilon by 2. So how much can you change by another epsilon by 2? So you have to be slightly careful at the boundary, like that you do it correctly. But otherwise it's fine. So and if it is not fine, change the parameters
between
and 2. Yeah. So something
so much and then
yeah. So you just pick the correct one and then. Yeah. So that's and so each time you're going to adjacent points and so.
So I guess the lazy way to do it is to just allow more possibilities here, allow it's above 2 also.
So, yeah, that's the usually allow us of 2 also. Then you're certainly fine. But then that will not remain Lipschitz. So what you
Okay.
It's not need to be a subset of.
yeah, that's true. Then I mean that will basically change the constant.
Yeah.
And so actually there's another so another way. So just a simple thing to note is that this thing is not so bad. So in the sense that if you have so if there is an epsilon net for S containing points in T, which is a superset of S, then there is an epsilon net, 2 epsilon net C prime for S containing such that C prime is a subset of S. Okay, so this is a generic fact you can just prove in any method. And so that's where you can do this trick with the two thing and at the cost of epsilon changing. But the crucial thing is that it's going to be exponentially more over epsilon, only exponential, not more. Yeah, so and that's what it is. Okay, so now with all this, so this is all a sketch. Okay. So now with all this, what do we get?
Things. Okay. We try to.
Oh, this thing is form. Yeah. Okay. So we get that for every epsilon positive, this E so sorry, what am I doing? E so F and F 1 over n summation fxi minus E fxi is less than theta 1 times so the other constant that is absorbed in the previous one.
No, not log 1 over epsilon. Yeah, no, I'm just making sure that everything else is correct. Yeah. Plus,
Okay. So now you optimize this and what do you get? Yeah, 1/3. Yeah.
if you get that this is less than theta 1 to the 1/3 by choosing.
So not quite, not that great. But yeah, but at least it's something. Like this is a priori not a thing. But at least you get that. So instead of n squared samples, you get epsilon error. It seems that you need only n cubes. Epsilon one other epsilon instead of one other epsilon squared samples. You get like one other. So the question is this the best possible?
So this is that is the right.
So the log factors, I guess it is.
One.
Up to log factors in n.
No, so actually, yeah. So the claim that it is not, we'll actually get all the way to root n for this problem, and so that's yeah. So yeah, so it,
Construction of that or it's actually.
no, no, it's not construction is correct. Everything that we need one more new idea. We need to do not just one epsilon, but all epsilon with all scales. It's a pretty powerful idea. It's a,
Sorry?
because for one epsilon, for one, you are able to one.
So that is just the lower one.
Yeah. So you can't hope to do better than that.
This is the exponent square root n is impervious to the class.
No, so no, no. So this was for this electric function. But I'm just saying, I mean, this is an example that is so because the chaining of the method that this kind of when you look at it, it looks like cheating. It's like why should it work? Would I XOR? So no other like it will be completely abstract from this. So all the function specific thing I've already done. The chaining method from this we have done all this stuff needed to apply the chaining method. We just need the main chaining method. It's an abstract.
So I guess Mother and Tanner would tell this.
Sorry?
The previous class. The last year.
Yeah, I think many times now. I think I also did it in the previous one, but yeah, but it's good to just do it many times. Yeah, this time I'll not be able to approve. I'm saying improve to variation and underlying the main is and this is and by using epsilon nets at all scales. This is a method known as chaining. This method is often called chaining. So what we look at is this special important results in this, which is called Dudley's inequality. Okay, so let B be a metric space. So this is going to be this abstract metric space, and be a set of
sub-Gaussian random variables. So it's a set of random variables, just not necessarily sub-Gaussian. I mean, it will be implied that they are sub-Gaussian, but say random variables such that for every ST in T, ZT minus ZS is C times dt ST sub-Gaussian. That is probability let me just write it like this. Okay, so these are random variables, but if they're indexed by the points in the but the thing is that they are sort of close in the sense, the corresponding points of sorry. So zero mean is not necessarily needed. Yeah, we'll see. So okay, so this is there, and then for every T0 in T, the expectation of soup. So yeah, so this needs a little bit of clarification, but let me just write it. So soup over all finite subset. So this is the definite, yeah. So over this. So this I've been maybe in the Lipschitz case it was clear, but in general this thing might be a bit silly, right? I like so this expectation of supremum or arbitrary set might not be measurable and so on. So the way you define it is to just take a supremum over all finite sets of the supremum over that set. So that, but let me just not worry about that. Oh, so sorry. Let me just not put this. This is K. So so just to because this just to differentiate things that actually come up in the algorithm, come up in the result, but from the things that strong. K times integral. Yeah. There is no absolute value anymore. So this follows easily from this. Because this also implies like without the absolute value is also bounded by this. And if you're mean zero, then E0.
Okay, at some point.
Yeah, so for any point you can do this. Yeah, so we'll see. Yeah, so this is only the trick is to what is the random. So, but is the statement here? So now we have to apply this. So what should I? Yeah, so that's what I was asking. So what should the points be? Then these points T etc. Sorry.
So T, right?
No, that's yeah. So that's the thing. It is what should be indexing variable for our example. So we have a set of random variables. What are the random variables indexing? We're taking some supreme or some random variables.
So points have to be the functions.
Yes, the points have to be the functions. There is the few change. So the point have to be the function. That's where we have our epsilon nets. And this sub-Gaussian thing is essentially clear. It's just clear. I mean, it's just because it's yeah. Yeah, so you just take the differences and maybe the K is like 2 or something. Maybe 2 less. Yeah, because of the not only the Lipschitz, just because of the
Your variables are now evaluation of the.
yeah. So let's just see what the variables are. So there will be random variables. So underlying random space. So the randomness is in the X.
Yeah.
So these get sampled once and for all.
Yes.
The random variable now becomes determining function of the space. And
Your T is actually your capital F.
Sorry?
So your space T is your capital F.
Yes, both will be capital. That's what.
Yeah.
And now
So tens of F would be some.
and there's some, and when you look at the difference, the Lipschitz, yeah, not the Lipschitz, there's a fact that they're close. Will tell you that each point they have to be like fx minus gx is less than delta. So each they are in the like it's holding inequality except that the interval size is 2 times the distance between f and d. So let's just write that down. So for our setup.
Yeah, but the distance, you know,
And so okay, so let me so we apply the second one. So these are also mean zero, right? So we get soup f in 1 over n. Actually, so
This aspect, it doesn't require IID. IID is just required to get a CT and a subjoint and
No, it does because here I'm using sub-Gaussian. So this, how did I get it? Sub-Gaussian? Because it's
just taxonomy of subjoinability.
yes,
You're done.
yes, yeah,
So IID is just. for-
yeah. This part there's no nothing idea.
Yeah.
The differences have to be.
So 0 if delta is greater than, I don't know, maybe 2 or something, right? And it's 1 over root epsilon theta. So I mean, if the distance becomes too large, then I can just pick anyone. It's actually just 1 is enough, I think. Yeah, 1 is enough. Just take the 0 function.
So in the previous example, we said delta will be epsilon or
Sorry.
so then the competitive prime or we said delta will be epsilon or
Which one?
This delta should be
No, this is not this is d, the distance.
the distance from x to
Yeah.
So the d was epsilon. There we put epsilon to be n to the minus 1.
okay.
But there's something missing still. One small trick is missing.
Yeah, actually,
It is not actually relevant, but that's not a problem, I think, right?
because minus x is there, and minus x is also.
Yeah, if it is there, then minus x is also there. So this is the same as taking up.
Otherwise, you might have to lose some extra factors, but here you don't. This is the crucial thing. Go from f to minus f, the random variable just becomes exactly the negative. That's the point.
So yeah, so we get. So any questions about what we did so far? So epsilon x, well, so nothing changed. All the specific properties were here. Whatever we did with the vanilla epsilon was here. That gives a weaker result. The crucial thing that is there is that you use all the epsilon. That's the only thing. And the proof of the Dudley inequality literally does that. It's not just all, it's not all the fronts. It's not exponentially decaying scale. So like 1/4, 1/8.
But how do you prove it?
Yeah, so I was trying not to do the proof. Proof is, I mean, yeah, so given this thing, the proof is not complicated. What you do is, so you forget about this arbitrary, So you say that, okay, I look at epsilon x at all scales. So you start, so it's okay, so it's a fine. So first thing is, so yeah, so one thing is that, okay, what does the sup mean when t is infinite? So it's like sup over some finite set, sup over all finite sets of t of the supremum over that finite set. So let's assume that the t is finite from it. So we'll get some bound, it does not depend on the size of t at all. So then we'll just the supreme knows it. So we're looking at expectation of supremum over t in S. S is a finite subset of t of this point. So we're looking at this Z, but for now it's not just that we don't want to do all T naught, but some T naught. Okay. So now because it's a finite set, it has a finite diameter. Okay. So in particular, there is a large epsilon, so if I pick that large epsilon, then it will be covered by just one point. And then there's some small, like there's some smaller epsilon. So if I put epsilon smaller than that, then every point will be its own. So there's a finite range in that sense. Okay. So you just divide this range into powers of 2. So you start off with some large. So you basically you look at all the responses of the form 2 to the power k, k is an integer, positive or negative. You look at the largest k, or the smallest k for which the net becomes side 1. That's one way. And then you look at the largest k for which the large side or whatever. Like so, you basically the first k when you start making it smaller, so that the epsilon becomes the same as the set. Okay. So these are the only cases. So the finitely many cases that you need to consider. Okay. So now what do you, so this the single thing that is what you just T naught. So that's your T naught. So now you're looking at x t minus x t naught. That's what you're trying to form. So now you break this. So this is why it's called chaining. So you say so the what is this? Because remember the lowest scale x t. So you now project. So if you project to the x t, it's just projects to itself because there the epsilon has the whole set. On the last side, it projects to T naught, any point it projects T naught. So it's like right now what you're looking at is xt minus x naught, but T has been projected to the largest epsilon and on one side and the smallest on the whatever, the smallest epsilon on the other side. It's a difference of 2 projections. So now you just put all the things in between, like projection to this one minus this one plus this one. Now each one of those is a sub-option random variable.
The projection.
No. So like so basically, what do you get it?
So let's just think about this. So very simple sketch is that. So suppose S subset of T is finite. Yeah.
Yeah.
Okay. Let epsilon I equal to 2 to the power for every I in Z. Let A max or I max be the smallest I such that n epsilon I st becomes equal to 1. And that I mean be the largest I such that n epsilon is equal to size of x. Okay. So these things exist, and what Si the epsilon I not s size.
So these SI might not be a subset of F, but that's not a problem. It can be in T, but that's not a problem. Don't worry about that. So there are two things to note. One is that what can I say about SI plus 1 in terms of SI? Has to be at least as large because these are the best possible epsilon. That one will also be. Okay. So this we keep. Yeah, and Si min is equal to Si max is equal to 1. Let T naught.
So this SI is what is the definition again? It is possible epsilon.
Sorry, is the best possible epsilon at that level in T. So it may not be a set of S, subset of S, but that don't worry about it. Just
Okay, such a set will exist.
well, just take them.
Yeah.
So it's a finite set. I mean, it's not a finite, but I mean, like you're minimizing some integer value function. So it will see which we know. A positive interaction. Okay, so this is and yeah,
So this is fine. And now let pi I of x be the closest element in Si to x.
okay. So ties both arbitrarily. This is the projection. So for any x, I go to the closest point in there.
Yeah, so then what you do? So then you just look at this. So you look at xt minus x0. It is just summation. So or rather, it's just x of pi I min or max min, right? Yeah, min. No, yeah, min. I mean,
So I mean, let's do this.
pi I max. Oh. Okay.
Yeah, just by definition, because the largest guy, everyone plays 50, and at the smallest one, everyone plays 2. I don't know which one I'm posing and was like
Index by any is a matrix space.
what?
T is index by a matrix.
Yes, P is the element. So I'm looking at arbitrary P.
So in the matrix space is a function, the index by a function.
Yes.
Yeah. Yeah. Okay, so this is there.
And so this breaks up.
Okay, let's go.
Plus 1, I think, right? Yeah.
I mean, plus 1.
Okay. So let's actually look at the absolute value. So absolute value.
And now you use several things. So it's okay. So this is the sum, and each one of these is sub-Gaussian. Okay, with a reasonably good parameter. Like basically, it has to be proportional to epsilon, because right. So 2 times epsilon that means. And how many such terms are there? Like across all the t's that I will choose,
Logs and plus.
how many terms are there? How many different such terms can appear?
Logs and plus.
So over all t,
For any fixed T,
how many for any t or for the like how many of these kind of terms x pi a t, like how many different pairs pi a t pi a plus 1 t can there be? Of course, it could be as big as the size of x, but I want to write it in something of the corresponding, like I. Yeah, mod s and mod s I plus 1, which is at most mod s I squared. So the thing is, so you have mod s I, which one is the smaller? Yeah, si plus 1 squared. Yeah, si plus 1. Yeah. So si plus 1 squared. Yeah. So but yeah, that won't work. Yeah. So each one of them. So so these are not. So yes, it's a fun. So it's so what do we want to say? So I'm trying to do the supremum, right? So supremum over this. So this is supremum. Each one of these is a so now I put expectations. So I put expectation of supremum, expectation of supremum here That's what I want to compute it. It goes here, here, here. So expectation of supremum. Yeah, over this. But what is this? So this is a supremum of SI squared many subgaussian random variables, each of which is subgaussian proportional to epsilon I. Epsilon I, it doesn't matter because of the example. Yeah, the epsilon I is the thing. So it's a, so then I know it. So what this is? So like yes, and we know, and it's a maximum of certainty. So E sup next sorry. Yeah, but right now we're doing for 1s. We're going to show that. Yeah, so that one. So yeah, so after that we'll put a super over S on this side also. It won't change things. There's just so let me for now just not worry about that and. Okay. So these the crucial here, the distinct number of pairs here is at most. So only many distinct elements. Right? Other they all otherwise. So, here, so what am I writing here? Okay. And they're all sub-Gaussian. So, but what? So the distance between x. So the difference by definition is the difference between pi and pi plus 1. But that is. So I go from epsilon I to t, that is at most epsilon I. I go from t to that is at most epsilon I plus 1. So the whole thing is at most 2 times epsilon I, which is at most 4 times epsilon I plus 1. So the whole thing is times k, or whatever the factor that was there. Right. So what does that mean? I know what each one of these is. So this is. Yeah, so the stat supremum doesn't count because that's what I was writing earlier. So supremum over the S is actually outside. You take the expected supremum over S and take the supremum of this over all S.
So you're saying that is upper
that's the definition of. So when I write expectation of supremum over in arbitrary sets, then that is defined to be I take the supremum over all finite sets of S of the expected of supremum in that. Okay, but now, so what is this? This we know, right? What is it?
That's what you're having more is.
And log of the number of things, like root log. And now we are done. Like finished. So this now after this just estimating the sum with the integral. So why is that? So epsilon I plus 1 was 2 to the minus I plus 1 or something. So 2 to the power minus
I plus 1 root log of
And it's not.
Yeah. And yeah, sorry.
Two points and someone should be in substance and epsilon.
oh yeah, that's like always. And that is anyway less than if I can put t here, right? Because
Yeah, if I have epsilon of t, I can that also have got S because that's why I was saying yeah. So right. So now yeah. So, but now what do you do? So basically you just like
so this you write it as 2 to the power I minus. So 2 to the minus I plus 1. Okay, so 2 to the power minus I plus 1, I plus 2, 2 to the power minus I plus 1 log n 2 to the power minus I plus 1 dt d epsilon times 2.
this is just saying that this is the integral from here to here should power minus x. But now the thing is that I can so this thing here, if I represent the epsilon, all the epsilon is smaller than this. So this n will only be larger. And that's it. So now you just so this whole thing becomes like
And it's and then this is just changing.
Yeah, and yeah, and so this I just because now I just go from 0 to infinity, that's certainly less than. Because these each of these
intervals is destroyed. Yeah. So the only thing I did not say is how do you choose this keyword, but that's easy. You just say that if you have one particular keyword, you add one more epsilon on top, like after the one. So there's one epsilon that got into the size one. You add one more on top, twice of that. That will clearly cover starting from any point. Because any point of within epsilon distance, and that so if you do twice that, then any point will cover that. And the only thing that we always needed is this thing, Si plus 1 bigger than Si. That is still fine because they are both equal. So you can do it for any inputs. Okay, so that's how, yeah, it's more or less the whole video. Sorry?
Like,
Yeah, because the point is when you think are very close, your other big epsilon might just not like might magnify distance. If two functions are very extremely close, closer than whatever the fixed epsilon you're choosing, then you're not taking advantage of the fact that they're very close. They're actually this says that okay, take advantage of this.
So in some sense, you are
The thing that your underlying domain is continuous. Things that are really close should really be much closer than any finite epsilon. Any one signal. The reason it's called chaining is exactly because of that. You chain the difference by going through smaller and smaller. Okay, so let's stop here.
So any pair of functions is being probed by the appropriate, but you had a fixed reference, you would have been probing each one of the same.